Hello, everyone. This is Mustafa. I'm going to be the presenter today for the FoundationDB paper. We have Alex Miller with us, so any question, please direct it to him. So at the beginning, we're going to define the FoundationDB as the paper actually defines it as ordered transactional key value store. They created it in 2009, so more than 10 years. And it got its popularity because it was one of the first systems that combines the scalability of NoSQL with ACID transactions. And I think most of the systems that were at that time searching for this combination, I think they were always going to FoundationDB. And I heard in a talk of Snowflake that they actually decided to use FoundationDB because of that reason, that they didn't find other DB at that time giving them the same flexibility. It actually also gave them the strictly serializable transaction, which is a very decent feature to have for a NoSQL. But we're going to know in the couple of slides how they are achieving it. And there is some limitation to it to achieve that kind of serializability for with also scalability. So FoundationDB solves the mystery of that we are not going to touch any higher level, and we're going to only focus on the lower level of the database. And then anyone wants to use the FoundationDB has to build layers on top of it. And that gives them a lot of variety of use cases. So you can use FoundationDB as a semi-relational databases or document databases, or even graph database, and there is like some examples for that. But most interesting example for me was that CouchDB is like, they are now working on like rebuilding all the system as a layer on top of FoundationDB. And we're gonna know why they have that decision, and why FoundationDB actually has a lot of future coming in, towards it. And it's already being serving Apple infrastructure and Snowflake. But Snowflake is using it for metadata. And you have to have that in mind, because when you look at how FoundationDB is architectured, you will start thinking how Snowflake is using it, because FoundationDB has actually should be very small key set, that and the transaction should be very fast, which is against everything Snowflake is doing. So that's why Snowflake is using FoundationDB as a metadata database. So we're going to start by touching some design principles that makes FoundationDB very special. First, and I think this is the most special thing about FoundationDB is they are using the unbundled architecture, which decouples roles of the database itself. So they have something called the control plane, and they have what's called the data plane. So the control plane, basically, in my opinion, it's what's holding the database together. So basically, it is a configuration system that have the metadata of the cluster. And we're going to see later that how this piece is the core of the database in my opinion. It uses the active disk access for high availability. So you can trust it that's available. If the quorum can exist, of course. And the data plane also, they separated it in multiple levels, and they have something called transaction system, which is an in-memory write path, and at that, this is where all the magic happens. And they have the lower level, which is the storage system. Actually, it's which is actually where the data got persisted for read. So if you can see the separate read and write, as we're going to see in a couple of slides. And the second most interesting principle about FoundationDB is that they fail fast and recover fast. And that's actually very interesting. And for me, it was, I couldn't think of a system can do that, that their whole design principle is, if anything happens, just shut down the system and reboot it again. And actually not reboot the same system, you're gonna deploy a new system. And they prove that it's working fast and it's working decently in the production. And they say that the mean time to recovery is around 5 seconds, which is very good, to be honest. And they made the recovery very simple, that you have only one recovery path for all the failures, or all reconfiguration and everything, which is, if you think about it, it's a very cool idea that you have one path for everything, that you can really well tested it and maintain one path. That's, I think that's cool. And the third thing that's very, they brag about it, and they have all the right to do that, that they have what they call the deterministic simulator, which they say that they built before they built the database itself. And this deterministic simulator is they try to, if you can see at the picture, they try to simulate all the moving pieces that can generate random behavior, and that to be able to will test their database and make their production very fast. And actually, it serves them very well. And I don't think that no one works for storage industry that hopes for something better than this. You know, this is like, if you have a well deterministic simulator that you can repro and get bugs out of it, that's a very good thing to have, to be honest. And then we're gonna move a little bit to the system interface, like what is the database actually provides us. So basically, they have the get and set for single keys and get range for range keys, because they are ordered database, like we mentioned before. And they have a clear, which is also a very good, nice API to have, that you have clear to, that you can clear range, you can delete a range from your database. And they, the over transaction, like we said, with strict serializability, but they have some limits. And these limits, arguably, you can look at as a limit, but at the end, they say that they it turned out to be not a limit, but a feature. We're gonna know how. So the key sizes and value sizes and transaction size, it's just something due to performance, and which actually tells you that it cannot work with large transactions. It should be small, it should be fast, small keys, small values, and transaction should be very fast. And one thing that you have to know about FoundationDB is the 5 second, because this 5 second, it's a limitation they put on themselves, and we're gonna know why. But everything in FoundationDB should happens or start and finish before 5 seconds, because all the history in FoundationDB is 5 seconds. It's like fish memory. It's only have history for 5 seconds. Aims is as we're gonna see later. And at the end, they say that they learned a lot from this 5 second. And even CouchDB, when they build their system on that, they say that they had to revise all their system to see why sometimes their transaction takes more than 5 seconds. So this actually 5 seconds transaction limit is actually, it's like they put the baseline for how the client should design their transaction, and they give them the right option for it. Like, this is a database if you want to have you know, the optimal time for a transaction, and it works very well for multiple systems. And but in a talk, in one of their talks, they said actually that they are now evaluating. I don't know if that is still on the road or no, but they are evaluating to change that. They are evaluating to add another storage engine. And this 5 seconds might change in the future, but I don't know if they're still doing that or not. And now we're going to move to the architecture, and we're going to have this picture for some time, so bear with me. The control plane, like I said, the one that used Paxos, the most important thing is called coordinators, and it's a disk Paxos group that should be always running. And they always trying to elect, or one of them always try to become a cluster controller. So it's a singleton. We have a multiple of singleton in this system. And this cluster control, because of Paxos, it's always going to be one. And it monitors all the servers in the cluster, and it recruits 3 singleton. One of them is the sequencer, and that sequencer is, to be honest, is the second important piece in the system, because we're going to see later how the system is very actually is depend largely on the sequencer itself, and some other 2 singletons, which is the data distributor and the rate keeper, something for monitoring failures and balancing the data, and actually protecting the cluster from overloading. But Beaver didn't talk much about them. And then we're going to move to the data plane, which is, like I said before, the FoundationDB target the workload that read mostly. That we're going to know why. And it should be small set of keys and have low contention between them. And if you want scalability, go to FoundationDB. And that, if you look at that, it actually matches a lot of use cases in our daily life. And if you look at Snowflake, that is the system that you were searching for the metadata. And then we're going to talk about the first or the most important piece of the data plane, which is the transaction management system. So the one thing that you have to know about that is the most important thing is it in memory, everything in memory in that system. And the sequencer, after it got recruits by the cluster controller, it recruits another three roles, which is the proxies and the resolvers and the log servers. And sequencer is role is to assign read version and commit version to each transaction. And we're gonna know how is this actually being contributed to the transaction later. Proxies is this is where the MVCD logic happens, and resolver is where the conflicts between transactions being resolved from the name. The log servers, you can think about them as write-ahead logs and the persistent tool storage. They are not in memory. And the storage servers is actually the main or the majority of the process of the system exists there. And reads, clients reads go there directly there. That's why you can scale reads as you can. Just add more nodes for the storage system. They are sharded. They have continuous key range each storage. And the storage nodes themselves, each one has a modified version of SQLite, and together they form a distributed B tree. And the MVCC data is stored in memory in the SS, in the storage system, which is, this is one important information that you have to know, that right now the engine of the storage system is unversioned, so it's only have one version. If you persist the data to the storage node, basically you have one version. So their MVCC is actually in memory, hence the 5-second window. So they keep everything for MVCC and for history in 5 seconds, and that's why the transaction cannot stay more than 5 seconds, because this means that we are not able to see what happened if it's more than that, because the history in memory is just 5 seconds. And I think if they change the underlying storage engine to support MVCC, I think that's only when the 5-second can change. I don't know how they're going to solve the resolver. We're going to see later, but I don't know. One thing that we gain from the unbundled architecture is you can scale each piece of the system independently of the other. So if you want to scale a scaling read, you're just adding more storage servers, because the client goes there for read, as we're going to see. And if you want to scale writes, you're going to add more processes to the proxies and the resolver and the log server. And both can, like I said, independently scale. Depends on how's the use case of your system and the contention and where the contention your system is having. From their experience, they found that the singletons that exist are not limiting the performance, and they are not a performance bottleneck, as they perform limited metadata operations. And of course, when you have a singleton, that simplifies stuff. And we're going to see how the sequencer is one of the most important thing in our system. And if it's only one process, so you have only one single truth table of your system, which is very nice. And I think this is one of the most things that simplifies their architecture. So we are going to talk now about the bootstrapping, how the system is actually got bootstrapped from the beginning. So one of the cool thing that everything exists in the system itself, so there is no external dependencies. So they use the storage system to save the metadata for the whole system and the user data itself. And then the metadata of the storage server itself exists in the log servers, and which is actually persisted. And the configuration of the log server itself, it should be stored in all coordinators, which they form the paxos with themselves. So we can guarantee that the data will not be lost on the coordinators. So if you think about that, all the metadata exists in the system itself. And the bootstrapping starts by the coordinator elects a cluster controller. And then the cluster controller recruits a new sequencer. So you can think about as a sequencer as a new transaction system, because the sequencer will start everything from scratch. So sequencer will read the configuration of the old log servers that's actually in the coordinator, and then spawns a new TS and LS, which is transaction system and log systems. So it will spawn new proxies, new resolvers, leaving the old system as it is. It will try to terminate the old system, but they don't care much about them, to be honest. As long as it can talk to the old log servers and get the persisted data on it. And then proxies will recover the system metadata from the old log server, and we're going to see how that's happening. And then the sequencer will wait till the new transaction system finish recovery, and then it will write the new configuration to the coordinators. And now, at that point, you can feel again, because now the coordinator has the new configuration. When they reconfigure, and this is also a very cool thing about FoundationDB, that, like we said, they have only one failure path. Either it's by, and we're not gonna call it a failure path, we're gonna call it a reconfiguration path, because whenever they detect a failure, they just reconfigure the whole system again. Basically they get to the bootstrap process and invoke it. And all that happens by just terminate the sequencer. So all what you have to do is, when you detect a failure or you have a new configuration, is just terminate the sequencer. And the bootstrap process will start up and get you a new system. And they call that an epoch. And you can think of epoch as a generation of TS and LS. And each generation has one unique sequencer process, which is very important, because sequencer is the one that actually does the versioning of the system. So right now we know how they bootstrap and how they reconfigure. And right now, let's see how they do their transaction. So you can split the transaction to two phases, right? A read phase and write phase. So the read path, first, the client has contact one of the proxies to obtain the read version. And then proxies does not have read version on themselves, so they have to go to the sequencer, and the sequencer, from the name, the one that actually have the global view of the system, so he can issue versions as a read version and commit version. So when the sequencer gives you a read version, it's guaranteed that it's not less than any commit version before. So you can see all the committed transaction before you. And then the read version sent back to the client. And now the client has a read version. So clients now can go directly to the storage servers if they actually know which storage server to go with to get this range of keys. And that actually also been fetched from proxies and can be cached on client. And if the client failed, he can go to the proxies again and get that piece of information with the metadata information, which shouldn't be changing a lot until the data distributor decided that we're going to rebalance. So the client now has a version and has what storage server they can go to, and they can go directly to the storage servers or storage system to keep reading from there. So we have two types of transaction. We have a read-only transaction, and we have a read-write transaction. So read-only transactions can end there because their commit actually happens locally. They don't have to send it to the system and invoke the commit process. And that's why you will always find that read is more fast than write. And that's why this system is a read-heavy system. Because you only need one piece of information, what is the read version, and you just go directly to the storage system. And I think, of course, they have that you might not even need a read version. You just can go to the storage system directly and read whatever persisted there. If you don't care about the MVCC 5-second window that exists on the storage system. Like we said, the storage system has an MVCC with 5 seconds range and has a durable committed transactions on the system itself. And then if you have a transaction that has writes in it, so you have to go to the write path, which is first the whole write, all writes going to be buffered, and it's only going to be sent at the commit time. Of course, write-read conflicts going to be solved at the client itself. So all you can read sorry, not conflicts, you can read your writes from the client itself. But writes only send at the commit time. So at the commit time, the client sends the whole transaction data itself, which is we have limit on the size. And then they send the whole read set and the write set that being and the read version to the proxies. And then the proxy go to the sequencer and say that I want a commit version that should be greater than all the read version or commit version that happens on the sequencer itself. And then the proxy sends this transaction information with the commit version to the resolvers. And the resolvers are range partition. So each resolver serves one range of keys. So you have to send it to the whole resolvers. And the proxy should wait for all resolvers response to commit or abort an transaction. And the resolvers implement optimistic concurrency control, and it checks for read-write conflicts from its in-memory 5 seconds. And this is where the 5 seconds comes. So resolvers maintain history in memory for 5 seconds for the whole transaction that happened before. So basically, they look at your read version and the write version and see that if any of your keys change in the middle, and they detect the conflict there and they abort your transaction, and just the client has to redo it. And then if all resolvers commit this transaction, they will send it back to the proxy. And then the proxy sends this transaction to the log server. Log servers also being partitioned. So each log server has some key range. And So proxies send a message to all log servers, as we're going to see. But keep that in mind, that the log server are partitioned, but on the commit, the proxies send a message to all log servers. And then the proxy reports the committed version to the sequencer to have this information. And then the proxy replies to the client. At that point, the data didn't reach to the storage system because it's not a synchronous call. It's an asynchronous. So the storage system continuously pull the mutation logs from the log system, from the log servers, and apply the committed update to disk. So after we saw how the write path and the read path happening, we can visualize how the strict serializability happens. It's by combining the optimistic concurrency control and MVCC together. And this commit version that the sequencer sends, it's actually defines a serial history of transaction that it imposes an order on each transaction. And you can look at this write version or the commit version as a log sequence number that each transaction has. And the log system has this transaction or this mutation in increasing order of LSN. And the storage system also applies this each transaction in increasing LSN numbers. They say that resolver is not a bottleneck because it can handle up to 280K transaction per second, which is a very high number. And because of its partition, so all the ranges can be happening in parallel. But there is one drawback for the resolvers. As we mentioned, the resolvers are partitioned. So, and the resolver does not know about the response of other resolvers. So one resolver range cannot detect the conflict, so they will commit the data. So they will update the in-memory data they have with the read set and write set commit version. And that might in the future say that a future transaction is being conflicted, while it's not, because that range that the resolver commit actually aborted from another resolver. And they don't fix this, to be honest. They just say that it doesn't happen regularly in their production system. Because they say that their workload most of the time has low contention between each other, and transaction does not conflict much from their production. And this 5-second window makes it very hard that transaction conflict with each other. But this problem exists there. But if you think about it, all what it will affect is that the client will retry the transaction which still, when we see their evaluation, it's not a big problem for them. After the proxy, like we said, commit gets the commit from the resolver, it will send, if you can see here, it will send the transaction data to the log system. But we saw that the proxy sends the message to all log servers. So the proxy has a map, and that map say that which log server has which keys, which is in memory. And then each transaction has a common header, which is what is the LSN right now, and what is the previous LSN, and what is the non-committed version till now. And then they send this data to all the log servers. but they don't put the data to all log servers. They only put the data, which is the keys and values, only to the log server that gonna have these ranges or can serve these ranges. I think it's a performance maybe optimization. But they persist this information, which is last known committed version, to all log servers. And then when all log servers reply to the proxy that the log data is durable right now, so now the proxy can update its own committed version to the LSM if it's larger than that. And now the new KCV is now updated, but it's still on the proxy. It's not on the log server itself. The last step is that the storage server pull the mutation from the log servers and applied it. And someone can arguably say that trying to read your writes might fail because of the lag. And to be honest, they have a very small lag between the LS and SS. And you can see that from the graph that the average is around 3 milliseconds or 4 milliseconds, and the maximum can go up to 200 milliseconds, which is very good like time to have your writes. And client, when they don't find the read, when they don't find the updated they have a read version, and they issue a read with that read version, and they didn't find it. All that is, you're gonna reissue a new read, and they will find it at that point because of the low lag time. They have some optimization that the storage server can buffer the updates in memory and only persist it with a longer delay, and they try to improve some I/O for their storage servers. They have a very nice recovery system that basically, if you need to recover the system if it fails. So first, if you detect a failure, you will issue a new like you will hit the new reconfiguration path, like we said. So basically, the new sequencer will start the whole system, and it's zero recovery for the new system that just built. It's not like the traditional recovery method, which is there is no checkpoint at that system. There is no reapplying or redoing or undoing logs. Basically, the sequencer, when it tried to recruit a new transaction system, the sequencer tried to terminate all the log servers. And it takes from them the maximum, like we said before, that each log server have this information persisted. So the sequencer basically gets this information from each log server. So basically, it has the maximum KCVZ received and the maximum durable version as they have. And the durable version is actually the maximum persisted LSM, which when you look here, the KCV is always less than the new LSN, of course. So these two information get back after it persisted at each log server, they send it to the new sequencer. And now the sequencer has to decide how they're going to recover the system. So basically, they get the maximum of all KCV and say that this is the previous version, or what they call the previous epoch end version. And then they have something called RV, which is the minimum the minimum of all DVs, and that range, which is the that data that exists between the BV and RV. This is the data that they need to redo again on the new log servers. So they copy the data from the old log servers to the new log servers between these two range, basically between the BEV and the RV. And they say that this time is not this step shouldn't take much because it's only seconds data. Because if you think about it, it should be less than 5 seconds. All the data between the BEV and the RV. And so now they recovered the new log servers. But when you think about how they're going to recover the storage server, if you remember that the storage server only have the committed data, so all the key CVs already been committed, and all the new data which was in flight for MVCC, it's still in the memory. So all what they do is actually they discard the in-memory multi-version in the storage server, and they just reapply, or they don't do something unique. It's just let the storage system refetch the mutations again from the log servers, as always, starting from BEV +1, and they will go with the new transactions. So during this time, the system can actually accept the new transactions because nothing can stop it from that. So basically, their recovery is just reset the system and make it go and make it do the regular process. Just had to copy some seconds data from old log servers. After that, they talked about replication, and they have geo-replication also, but I will leave that for you to read. And then I will go directly to the evaluation. So first, we're gonna look at the production measurement they have. They did that on the Apple production. They have a geo-replicated cluster. And if you look at their evaluation, the figure of on the left actually showed the average number of read operation and write operation, and you can see that they were able to reach on average to 400K, around 400K, and the write operation they can reach up to 150K. And if you look at the latency that clients can see, you can see that the read latency are very small. It's around 1 millisecond up to 19 milliseconds, which is very low. And the commit is around between 22 milliseconds and 300 milliseconds on the maximum, or 99th percentile. Also, they achieve a good throughput that can scale by increasing the number of machines. If you look at the figure of the left, they actually for a 100 operation per transaction, they were able to achieve 5x by increasing the machine itself from 4 to 24 machines. And that's for the write throughput. And if the transaction has more than like more than around 500 transaction, they have or transaction has more than 500 operation per transaction, you can achieve 6x scalability. For read throughput, they achieve 3x and 4x by increasing the machines. At the figure on the right, they show the operation per second for read-write traffic for like 90-10 read-write traffic, which increased around 5x. And you can see that at the end it will saturate because resolver and proxies will be CPU saturated, and you can see that actually here where they try to increase the number of operations per second, the latency will exponentially increase because of the saturation of the system itself. I think also the throughput increase with the number or in the operation per second increase. And you can see that the reads have more throughput than the writes, of course. And you can see that the commit is the one that actually saturated very fast because of the latency of the queuing time for resolver and proxies going to be saturated at the end. They say that around 2 million operations, the resolver and the proxy will saturate. And at the end, of course, their magic reconfiguration, they say that it happens very fast. If you can see that actually the median is around 3 milliseconds and 3 seconds, and the maximum can reach to up 5 seconds. So you have reconfiguration or detection is less than 5 seconds on most cases. They actually reported one case that has 9 seconds, which still achieves their 5 times availability. And that's it. Thank you, and sorry for being long, taking a long.